Okay, so continuing with the tutorial problems. So I want to today discuss something called Curie susceptibility. So Curie susceptibility involves the interaction of spins which are quantized. So that means quantum spins in a magnetic field. So, so the point is that now instead of thinking of spin half or spin 1 or anything specific, so we make it general, but then it remains quantized. So in other words, we consider a general spin S. So that means the projection of the spin vector in any direction is going to be either minus s times h bar or minus s plus 1 times h bar all the way up to s times h bar. So if you look at this sentence, so it's so you see that the spins projections are quantized in this manner. S is the spin quantum number, which can be integer, like 0 is uninteresting, so it can be 1 and 1 2 3 4, or it can be half integer, like half 3 by 2, like that. Now this when it's in contact with a magnetic field, so when there's a uniform magnetic field, the Hamiltonian is going to be minus is basically Hamiltonian is going to be minus b m, b is the magnetic field, times m z. Okay, so this is the Hamiltonian. So so the idea is to calculate the partition function and then expand in powers of b, and then because of this you will be able to calculate the well, independent of this you can calculate the magnetization and calculate the linear susceptibility, and then show that the susceptibility obeys Curie's law, which is basically constant divided by temperature. And the goal is to also find this constant in terms of the other parameters in the problem. And then these are fairly trivial, but what is interesting is the last question here. So by the way, these questions, like I told you, are from MIT open courseware. So so because I wanted to introduce some challenging, interesting questions which MIT open courseware has a number of them, which are very interesting and challenging and important. So it's worthwhile studying them. So even though I'm not inventing new questions, but I'm telling you how to solve them on my own. So all right, so so the interesting part of this question they have asked is, show that the specific heats when you hold magnetic field fixed or when you hold the magnetization fixed, they are different. So you can change temperature holding magnetic field fixed, which is easier, but you can also do the other thing, which is change temperature holding the magnetization fixed. So and you can ask yourself what is the specific heat in each situation, and they are going to be different, and so we are asked to show that the difference between these two is precisely this constant c times b squared by t squared. Okay, so the question is, how do you do this? Okay, so let's try and see if we can do this. So in order to do this, the first thing we have to do is calculate the Gibbs partition function, which is it's as simple as z t b is basically the summation over all the m's times e raised to beta mu b mi summation over I. Okay, so this is going to so using the idea that you can flip the order of taking the trace. So this is taking trace, and this is so there is a summation in the exponent. So if you can interchange those two, So this is going to be something raised to n, and that something is basically m goes from minus s to s times e raised to beta mu b m. So it's going to look like this, and the answer is going to look like this. Okay, raised to n. So of course this is a simple geometric series which you can do and get this answer. So I prefer to do this on the computer. So there, like I told you, I use symbolic algebra packages to do this. All right, so now notice that Z is given so the Gibbs free energy. So in terms of the Gibbs free energy, you can write the partition function as follows. So from this you can deduce the Gibbs free energy itself as minus t times n times log of this quantity there, cosine hyperbolic s beta mu b plus cotangent beta mu b by 2 times sine hyperbolic s beta mu b. Okay. So now the question asks you to expand in powers of the magnetic field. It asks you to expand in powers of the magnetic field and explain how the leading terms look like. So if you expand this out in powers of the magnetic field, it's going to look like this. Okay, so that's what it looks like when you expand it out. And the magnetization itself, it's kind of easy to find. So the magnetization, you see, notice that there is an e raised to beta mu b times sigma I equals 1 to n mi. So actually so there is this term in the partition function. So this is basically the partition function. So now you see, this is your magnetization. So if I want to find the average of this, what I have to do is I have to bring this. So it's basically trace of, so the average of magnetization is basically trace of e raised to b mz over trace of e raised to b mz, where mz is the sum over all of them. Okay, so the question is, how do you do this? So this is clearly basically, if you call this z, right? So that's the basically take the log beta b and log z, and you differentiate. That's what you get. All right, so I'm going to do this. So remember that we just derived z. So or you can write this z as log z. So this means basically log z is minus beta g. So this is nothing but minus beta g. So if you think of differentiating with respect to magnetic field, so this becomes minus dg by dB basically. So that's what that is. So the average magnetization is nothing but the derivative of the Gibbs free energy with respect to the magnetic field. Okay. So so let me go ahead and do that. If I do that, I get this result. So because I have already calculated, so recall that I have already calculated the Gibbs free energy, and this is my Gibbs free energy. All I have to do is take a derivative with respect to magnetic field. Of course, it's more, I mean, I could get the general formula which is uninteresting, but I am going to use this. So if I use this, I get this result, which is basically 1/3 s into s plus 1 times beta b mu squared. Okay, so that's going to be my magnetization. So for small magnetic field, B is small. So the linear susceptibility is basically defined as the magnetization for small magnetic fields and the rate of change of that with respect to so the slope. So mz is going to be proportional to the magnetic field for small magnetic field, and the coefficient of proportionality is called the susceptibility, the linear susceptibility. So this comes out as C by T, where C is the Curie constant, which is 1/3 s into s plus 1 times mu squared. So that's one of the questions that was asked. So this is all fairly straightforward, but what is more interesting is the last part. Okay, so the part D was show that if you have a constant magnetic field, the specific heat is going to be different from what it is when you have a constant magnetization, and the difference between the two is basically given by this this result. So let's see if we will be able to derive this. So the question is, how do you derive this? So you see, in order to derive this, so we perform a Legendre transformation. So remember that you have the Gibbs free energy, which depends upon temperature and magnetic field. Okay, so you can choose to trade the magnetic field with magnetization. So remember that I have explained to you in great detail the geometrical meaning of this transformation, which is basically your suppose you have a function of a quantity like the magnetic field. You can either define it or you can either describe it by providing the values of B and values of G. So that's like the usual way. The other way is to provide the value of the slope and the intercept of the tangents to that curve. So G versus B is a certain curve, and you can either describe the curve itself through its x and y values, that means your ordinate and abscissa values, or you could you choose to define it in terms of you can describe that curve using a family of tangents. So by specifying again two numbers, one is the intercept and the other is the slope. So if you provide the slope and intercept, then you can, the straight line is unique, and then if in addition you postulate that has to be tangent to the curve, so that it makes the straight line completely unique. So providing a family of such straight lines gives you a alternative description of the system, different from what it is by providing Gibbs free energy. So as a result, so let's do the Legendre transformation, and it's done in the following way. By so imagine that I focus my attention to some particular value of magnetic field, and this is the definition of magnetization, and then I can create a, so if you have you know so imagine you have something like this. So this is your B star. Okay, so you have a whole bunch of slopes here. So the idea is that you create a straight line which is tangent to this curve. Okay, so the tangent to the curve is going to look like this. So, I am going to define the tangent to the curve. It's kind of defined with a negative. So, I am going to think of it as mz times b minus b star plus the value of b at b star is g. So, this is how I choose to define that straight line. So, the tangent to the straight line, so mz is the slope of minus g versus b, because there is a minus sign there. Okay. So, I am going to have to put minus sign there. Okay. So, now this makes sense, because at b equal to b star, y b equals minus g, okay, b star, and y dash b is basically mz, which is the slope of minus g versus okay. So, so if this is the case, then the free energy is going to be defined as the negative of the intercept. So, it is going to be defined as the negative of the intercept. So, I define the free energy as y at 0. So, this is going to look like mz times minus b star minus g of b star. So, the new free energy at constant magnetization is now going to be g at b star plus mz b star. Okay. So, that is what that is. So, now let us go ahead and see if we can calculate. So, so as a result, you see that the specific heat at constant magnetic field by definition is this. So, it is the derivative of the Gibbs free energy with respect to temperature, and the derivative of the constant of the free energy with constant magnetization is going to be with respect to the temperature is going to be the specific heat with respect to when you hold the magnetization fixed. So, these are two different types of specific heat. This specific heat is when you hold the magnetic field fixed and vary the temperature. So, that means B is fixed and you are changing temperature, you get a specific heat. So, you are supposed to differentiate the corresponding free energy. So, when you hold the magnetic field fixed, the corresponding free energy is the Gibbs free energy, and when you hold the magnetization fixed, it is a different free energy, which is the Legendre transform of the Gibbs free energy, and it does not have a particular name. So, it is some kind of free energy, and so it is the free energy corresponding to the situation where the magnetization is fixed. So, when the magnetization is fixed, you get a different free energy, and if you find the rate of change of that free energy with respect to temperature, you get a certain specific heat, and that is called Cm. So, now we will have to calculate these kinds of free energies, and so how do we do that? So, to calculate this, you see I am going to do it this way. So, this is my free energy when the magnetization is fixed. So, remember that I am only interested in the situation where the magnetic field is small. So, I am as a result allowed to expand in powers of the magnetic field. So, when I do that, so remember we did that for Gibbs free energy and we got this result. So, it is G of 0, which is something uninteresting. Well, it is I mean let me write it down, because it also depends on temperature, G of 0. So, it is going to be minus Nt times ln 2s plus 1 minus n mu squared over times s into s plus 1 times over 6t times b squared. Okay. So, that is my G of Bz. So, then I have to multiply or add to this, namely this quantity. Okay. so B times mz. So mz is 1/3. So if you remember, mz was I'm going to write it here, plus 1/3 1/3 s into s plus 1 times b mu squared by t times b, because there is a times b. So this is mz. So mz times b. So that's going to be another b squared. So you see that it's the same thing. This is minus 1/6 and this is plus 1/3. So that means this is basically this whole thing put together becomes plus 1/6, right? Because this is going to be 2/6 minus 1/6. So this is plus 1/6. So I might as well simplify it this way right here and get rid of this altogether. So that's going to be my new free energy. Now if I differentiate with respect to temperature, okay, so I get so if I differentiate df by dt, so that's my Cm. So that's going to look like minus n ln 2s plus 1, then it's going to be minus 1/6 minus n mu squared s into s plus 6t squared b squared. Okay, so that's what that is. And if I take the Gibbs free energy, and so remember that Gibbs free energy was this one. So this was Gibbs free energy. So if I take dg by dt, I get Cb. So that's what that is. So if I take dg by dt, I get the same thing with a plus sign for the second term. So that means Cb is same thing here, but the next term is the same thing with a different sign, with the opposite sign. Okay. So the question says show that Cb minus Cm is basically C times b squared by t squared, and where C is given by psi equals Ct, C by t. So this Curie constant. So we know that the Curie constant, we just calculated the Curie constant, if you remember, as 1/3 s into s plus 1 times mu squared. So now let us subtract this with this, so rather this with this. Okay, so if I subtract this with this, I get you see I get exactly this. So this will cancel out. So Cb minus Cm, so these two will cancel out, whereas this will add up. So it becomes n mu squared into s plus 1, okay, over 3t squared times b squared. So that's basically what it is. Okay. Well, there was a per particle, never mind. So there was a per particle. You can define magnetization per particle. So but point is that that's what this is. So it's C times b squared by t squared. So this is an interesting problem because it kind of explicitly forces you to think of the Legendre transformation, and that too in this peculiar context where normally in Legendre transformation you are trading energy for temperature. Like you are going from, suppose you are going from microcanonical to canonical ensemble. Typically what you do is you have a system with fixed energy, and a Legendre transformation will tell you how to transform the entropy, which is the fundamental quantity in the microcanonical ensemble, to the fundamental quantity for the canonical ensemble, which is basically the Helmholtz free energy. So it so Legendre transformation enables you to connect these two potentials, the microcanonical potential, which is just the entropy, and the canonical potential, which is Helmholtz free energy. So the connection between these two is established using Legendre transformation. But then, so in a less familiar context, the Legendre transformation is introduced in this particular problem, where you start with the Gibbs free energy, where you fix the magnetic field, and then you ask yourself, what would things look like if you choose to fix the magnetization instead? So given that magnetization is the slope of the Gibbs free energy with respect to the magnetic field, so this is a interesting and valid question to ask. Okay, so that is as far as this problem is concerned, and we'll discuss some of the other questions subsequently. Okay, thank you.